Welcome back to Multigrid Methods. Today we're going to continue our journey through Chapter 7, talking about the cell-centered finite difference method and how you do multigrid for that. So last time we almost finished with slide deck 1 from this chapter. I think there'll be 3 slide decks in total. And we made it almost all the way through. We were discussing this idea of the first smoothing property. So let me remind you of the result that we started trying to prove. So the first smoothing property essentially says this. So KL is our error transfer matrix for the smoother. We're assuming we do M1 smoothing iterations or smoothing passes using that smoothing technique, whatever it is. In this case, it's the Lambda Richardson's method. So this was that smoother where we characterized it in some sort of generic way with some free parameter omega, and Lambda Richardson is characterized precisely by choosing omega equals 1/2. So what we want to show is that there's some constant c greater than 0 such that for any number of smoothing passes we want to do, and for whatever vector we want to apply this smoothing to, WL in RNL, then the AL squared norm, that's kind of the, as we've said many times, it's the norm, the discrete norm, which is like a Sobolev 2 norm. So the Sobolev 2 discrete norm of KL raised to the M power, so M1 power, so that means doing M1 smoothing iterations applied to WL is less than or equal to a constant, which we can actually determine to be 1 over square root of 2, times the square root of the spectral radius, lambda, capital lambda L, divided by M1 times the AL, or the energy norm. This is also like the discrete Sobolev norm of the WL vector. Notice that the error goes down as M1 goes up. So as we do more and more smoothing iterations, this goes down to 0, right? Because that's in the denominator. So this is what's called a smoothing property. So again, we're using lambda Richardson smoother. So how do we prove this? Well, uh, so the first thing that we want to do is let's unpack the thing that we have on the left-hand side. So that unpacks, if we square that, as just some sort of inner product. So we said before that the AL norm, AL squared norm, can be rewritten as the Euclidean norm of AL times whatever vector is inside or whatever vector we're norming. So this is by a simple identity that we argued for last time. If it's the Euclidean inner norm squared, then that's the Euclidean inner product of the same vector with itself, right? So that's the inner product of that vector just repeated. Now what we're going to do is use an eigenvector basis of AL. So let's write WL in an eigenvector basis consisting of those the standard eigenvectors of AL. So these are just sign modes. All right, so that's our standard basis. That's the basis that we established previously, or the standard set of eigenvectors. Now, you can, of course, choose other eigenvectors if you want to, and you can normalize them any way you want. So we're going to just use the standard normalization that came from just the result that we proved earlier. We're not going to normalize them in any kind of special way. So these are just sine, k, pi, blah, blah, blah. All right, so now we know what that normalization is for those vectors if we use the standard eigenvector basis. So the normalization constants are going to be what we denote as beta LK. So L is the level number, right? And so we're going between 1 and NL. So for K between 1 and NL minus 1, the normalization beta works out to just be NL over 2. And for K equals NL, it's just exactly NL. This is a little bit different than what we found for the eigenvector basis for the standard uh, stiffness matrix. So remember, our AL matrix in this cell-centered case is not quite the standard one because it has that weird 3 on the diagonal in the first and last positions. So it has a 3 rather than all 2s. Okay, so let's continue. So this is the thing that we unpacked previously, so we're just going to use that. Now I'm going to use the basis here and here. And once I multiply by these operators onto that vector, which is expanded in this basis, then we start freeing up a bunch of eigenvalues. Okay. So remember what it means in particular, if we multiply AL times VLK, then we precisely get lambda VLK. Actually lambda K. And similarly, if we multiply the KL matrix times VL, we argue that for the Richardson smoother, its error transfer matrix has the same eigenvectors. And we called those eigenvalues, we called those mu LK. And of course, if you look back and see what mu it's a function of omega, but we're choosing omega equals to a half. And so we have that. All right, so whenever we multiply these operators times this vector, we're going to liberate for each k a bunch of different eigenvalues. All right, so I leave it to you to confirm this calculation. The fact that we're applying M1 smoothing passes means that we get a power 2 to the so power which is equal to 2 times m1 for this eigenvalue. And this eigenvalue, the eigenvalues for the standard stiffness matrix, this eigenvalue gets squared, and WLK gets squared as well. Those are the coefficients that you see here. Now, normally I would say be a bit more careful here, and maybe these should be modulus squared, right? But everything in sight is real vectors, and the expansions are all real. So we don't have to worry about complex modulus. Okay, so that's where all those terms come from. And now you have to be careful because whenever we do the term by term inner products of these vectors, let's see here. So those vectors are going to be orthogonal, but not orthonormal. And most of those vectors which hit each other in these expansions. So we're going to take this expansion and write the index k and maybe do one where we use index j, and we put them in here, and then we get these pairwise interactions between these eigenvectors, basically the dot products of different eigenvectors. Most of these dot products are going to be equal to 0 because we're going to use the orthogonality property, but the diagonal ones, whenever k and j are equal, involve the normalizations, and the normalizations we argued were just this. So that's where the normalizations come from. Right. So, or at least here. The next thing I'm going to do is I'm going to divide. Let's see, I want to establish this with an equality here. So I want to divide everywhere. Well, actually, it's even simpler than that. You're just going to pull out a common factor of the spectral radius. Remember, the spectral radius is the largest eigenvalue of the stiffness matrix. Well, if I pull out a factor here, I'm going to basically just create one by dividing it here. Okay, I'm going to leave it in there. Now, this is precisely the definition of mu Lk. That's the eigenvalues for the error transfer matrix for Richardson's lambda Richardson method. So that is just exactly, is that right? Is that right? Let's see. Let's make sure. Yeah, that's exactly right. Okay. Now what I've done here is I've taken one of these factors and both of these factors and I've moved them out. So that's where this comes from. This appears there. And so now notice that I have just one factor of the usual eigenvalue for the stiffness matrix divided by the spectral radius. Well, remember these are all positive numbers, and this is the largest of those positive numbers. So all of these numbers here are just fractions, numbers which are less than or equal to 1. And it's only equal to 1 in the case where we're dividing by the largest one of these guys. So that's the eigenvalue associated to k equals nl. And in this case, it's exactly equal to lambda L. So we just have a 1 whenever k is equal to nl, but otherwise we have numbers which are less than, strictly less than 1 and greater than 0. And here we have numbers which are, this number is of course 1, and now whenever k is equal to nl, this number becomes exactly equal to 1. So this number goes to 0, but otherwise these numbers are greater than or equal to 0, right? Actually greater than 0. So less than 1, so and greater than 0. All right, and then raised to some power. This we're going to keep on the outside for just a second. Okay, so now what do we want to do next? Well, I'm going to replace this guy with some. I'm going to call that a function, and then I'm going to bound that function, and that's all done in the next slide. But everything else I'm going to leave here. So this is just some. It turns out, based on work that we did way back in chapter 4. Was it chapter 4? Yeah. So way back in chapter 4, we encountered this thing previously, and so it's just if we can put this in some sort of box, writing this as something like a function x times 1 minus x to the 2m1 power, where x is between 0 and 1. We're going to give that function a name. I forget exactly what we called that. I don't think I did give it a name here, but in any case, call it the function f if you want. Well, this function f actually has a bound, okay? And the bound depends on a couple of things. Specifically, it depends on the size of m1. And so we're going to say the bound on this guy is just what we're going to call gm1, the maximum value. Okay, so we want the largest possible value. We're going to replace this by the maximum, and everything else that's left we're going to just leave inside of there. Well, actually what's left is fairly easy to show. Is just going to be the WL, the norm of WL in the AL norm, should say the AL norm or the energy norm of WL squared. And then of course that bound that we're going to mention in a moment. And then this guy was already out front, and that's independent of K. That's the spectral radius. Okay, so if I can establish this bound GM1 on this, and we're done. Well, we can call, let's see, GM1. Yeah. So I'm going to call the bound on that guy, I'm going to call G. And this guy here is just some function. That function I could call anything I want, like f of x or something like that. And I'm going to maximize this over all of the numbers which look like this and this, okay? So you see that's variable. And well, what's going on here? So these numbers, as we said before, are numbers that are we can call them x if you want. They're between 0 and 1. But they're discrete numbers. So it's a set of NL discrete numbers. And somewhere along the way, we're going to hit the maximum of those. Okay. Otherwise, this function is just positive. Now, we had a lemma from an earlier chapter. In particular, it was chapter 4, which said that this GM, which is the max of this, is less than this function. Now, where does this come from? Well, this function here is exactly, or I should say this function here is exactly this function, but we're making the variable, instead of being discrete at these NL values, we're just going to make that a continuous value. Well, if I have a maximum for these discrete values, I certainly also have a maximum taken over these continuous values of x going from 0 to 1. Now that value is much easier to find, the maximum of that guy, because I could just use calculus. I can take the derivative, set it equal to 0, show that I have a function which is let's see, in this it has to be concave, and I can easily find the location of the maximum, plug that back in, and find that the maximum is equal to 1 over 2 times m. Okay, for any m that I want to put in here. So you can see the maximum depends somehow on m. Well, now that gives it to us because this gm was that maximum. We know that it's less than 1 over 2m. I have a gm1 here because I did m1 smoothing operations. And so I can replace that gm with that maximum, which is just going to give me a 1 over 2m here. But now remember, I have this as squared and squared. I guess I'll replace this last one. Now I'm going to take the square root of both sides, and that of course maintains the direction of the inequality. And so what I get when I take the square root is I get square root of 1/2, square root of the spectral radius at level L over m1. And then of course I had squares here on these two norms which go away. And so this is exactly the first smoothing property that I want. Now, remember that generally speaking, for multigrid convergence, we need more or less three things. We need a Galerkin condition, a Galerkin type condition in place. We need a smoothing property, and we need an approximation property. So this is just one of those components. We've established the smoothing property. What I'm going to show you in the next few slides is that we can obtain the other two properties as well with a kind of asterisk. So we can't exactly obtain the strong Galerkin, the standard strong Galerkin condition. We're going to have to accept a weaker version of that, or a lesser version of that, called the imbalanced Galerkin condition. And this harkens back to what we talked about in chapter 5. So that's one thing, in addition to this smoothing principle. So we have two now. And then the last one that we're going to need is some type of approximation property. So we're going to get those two things that I just mentioned. In fact, it's going to be an alpha weak type approximation property to be specific. So those are the next two things we're going to obtain in the next slide deck. So the alpha weak approximation property and some sort of Galerkin condition. The next thing we want to do is we're going to talk about what sort of prolongation and restriction operations or matrices operators should we involve in this cell-centered finite difference setting. We want to show that with a certain choice, we get the failure, or we find the failure of the standard Galerkin condition, but we are able to obtain an imbalanced Galerkin condition, which isn't quite nothing. So it's less than it's kind of less than what we would want in a perfect situation, but it's still something. And then what we're going to do is we're going to add some additional multi-level tools that is going to aid us in our analysis. And then finally, we're going to establish the alpha weak approximation property. So that's going to give us our three components that we need to prove the convergence of this multigrid method. So we always need some sort of Galerkin condition, some sort of smoothing property, which we just obtained, and then some sort of approximation property. So those are the three key components. We have one, we need the other two. So this is the second of 3 slide decks on cell-centered finite difference methods and how we apply multigrid in this context. And we need to talk about, before time gets away from us, what we want to do for prolongation and restriction. And then, so once we make those choices, we want to check see if we have the Galerkin condition. We're going to find out in this case, we don't have the standard strong Galerkin condition, condition G0. The best we can do is some sort of imbalanced Galerkin condition, which isn't nothing. It's something, and it's still going to allow us to prove convergence, but we have to work a bit harder. So the idea of course, of prolongation and restriction is these are operators or matrices equivalently, which move information from coarse grid to fine grid and fine grid to coarse grid. So how does it go? Prolongation takes us from the coarse grid and it moves information up to the fine grid. So that's what prolongation does. And restriction is just the opposite. It takes information from a fine grid and it's going to move it down to the coarse grid. So here's a typical 2-level grid. We have some fine grid, and in this case, it has exactly 8 degrees of freedom. NL equals 8. We have these interior vertices, which are called cell-centered points. And of course, we have 2 ghost cells, as we've talked about. That's on the fine grid. And on the coarse grid, we have exactly half the number of degrees of freedom. In this case, NL equals 4. We also have 2 coarse grid ghost cells. Now, ghost cell points, or the values of the ghost cells, I should say, are usually always filled with some sort of boundary conditions. So they're not really degrees of freedom. The degrees of freedom are really these interior nodes. So in this case, there's exactly an even number of them. There's 4 on the coarse grid and 8 on the fine grid. In any case, the prolongation operator, as I said, moves information this direction, and restriction moves information that way. All right, so this is basically saying exactly that. If we have a grid which looks like this, with 4 degrees of freedom on the coarse grid and 8 degrees of freedom on the fine grid, and by the way, this is my physical domain. In this case, we're in one-dimensional space, and so our domain, we said, was 0 to 1. So this is just 2 different grid representations of the same domain. So in that case, we have NL equals 8 and L minus 1 equals 4. So if we're to construct a prolongation operator, which is going to take those 4 degrees of freedom on the coarse grid and map them to 8 degrees of freedom on the fine grid. So what we know is that we're going to need to construct a prolongation matrix, PL minus 1, that has 8 columns, or sorry, 8 rows and 4 columns. So generically speaking, what we want is one which has NL rows and NL minus 1 columns. Okay, rows and columns. Now in this case, in the cell-centered finite difference setting, this number here is always exactly 2 times that number. Okay, so it has twice as many rows as it has columns. That's what we need in that last example. So let's do this completely generically. Suppose that I have the level number being between 1 and L. So by construction, NL is equal to twice NL minus 1. The cell-centered prolongation matrix, PL minus 1, that's kind of the definition, is a matrix that has twice as many rows as it has columns, and it is of the form precisely like that. So let me give you the pattern here. So the pattern says that in the first column, So let's look in the first column first. That's that guy there. I'm going to put 2 1s, one in the first position, one in the second position. What about the second column? In the second column, I'm going to put a 1 in the third position and a 1 in the fourth. And I can keep going in that pattern. In the third column, I'm going to have a 1 in the fifth position and 1 in the, actually, position by position, I mean the row. So in the fifth row and the sixth row, and so on, until I get down to the last one has a 1 in this position, a 1 in that position, and then in the last column, I have a 1 in row NL, what would that be? NL minus 1 and NL. Okay. So let's think about how this guy applies to a vector, right? So let's do a case where, let me do a quick example here because I think that could be useful. And where the heck are we? There we are. So let's add a page here. So let's do a quick example. Let's say that NL is equal to 4, NL minus 1 is equal to 2. So what would this look like? So we have 4 rows, and we put 1s in the first 2 positions, and we have 2 columns. And so that's what our prolongation matrix is going to look like. In this case, PL minus 1. All right, so now let's take an arbitrary vector from our course grid. Okay, so let VL minus 1 be some vector. So it's going to be VL minus 1, 1, VL minus 1, 2. And let's apply PL minus 1 to VL minus 1. What is this going to do? Well, it's going to say we're just going to take this matrix and multiply it times that vector. So all we need to do is resolve what are the components in the product. So there are going to be 4 entries or 4 components in the product. So the first 2 are going to be this. So in the first 2 positions, we have VL minus 1, 1, and VL minus 1, 1, right? And what about the second 2 positions? Well, the first 2 were gotten by taking this row and multiplying it by that column vector, and then that row times that column vector. We get the same product in both cases. What about the next one? I'm going to take this row and multiply it times that column vector. So VL minus 1, 2, and VL minus 1, 2. All right, so that's the resulting vector that's going to be in on our fine grid, RNL. Okay, in this case, NL is equal to 4. So let's think about what this is doing. I've got my coarse grid representation of a function that has 2 degrees of freedom. And those 2 degrees of freedom are defined at the cell-centered points. Okay, and let's say there. Okay, so this is my XL minus 1, 1, XL minus 1, 2. Now, what is a prolongation operator doing? Well, it's creating another function which lives in the fine grid. But notice that the degrees of freedom that live in the fine grid are precisely the same ones that live in the coarse grid. It's just kind of doubling them. So what happens is when I create these points on the fine grid, the degrees of freedom now are exactly the same as they were before. They're defined at the cell-centered points for the fine grid, which are indicated by these red points. And that is exactly what the prolongation operator is doing in this case. It's basically taking the degrees of freedom that I had on the course grid and it's doubling them and putting one there and doing the same here, putting one here and one there. Okay, but now notice there are 4 degrees of freedom on the fine grid. That's good. But really there isn't any new information because all I've done is taken this point and I've doubled it. So I'm not really creating any new information. I'm just kind of doubling the information that I already have. That's the idea of the prolongation operator. So I can represent the prolongation operator either through the matrix or through its action, the action of that matrix. It doesn't really matter. The idea is more or less exactly the same. So if I act with the prolongation operator on an arbitrary vector, then basically it's doing exactly what I just said. It's taking those degrees of freedom from VL minus 1 and it's just putting them in, it's taking 1 degree of freedom and just doubling it and putting it in um, two locations essentially. So that's the prolongation operator. What about the restriction? Now, normally we would say the restriction operator should be just the transpose of the prolongation operator, but that's not what happens in this case. So in this case, what we do is we take the transpose of the prolongation operator, and then we're going to multiply it by a half. All right, so we're not going to just take the transpose. And of course, this is going to, right away, it's going to break we know that it's going to break the Galerkin condition. So the question is, how bad does it break it? Because remember, the Galerkin condition required 2 features. It required a balanced restriction prolongation pair, and it required that the wrap condition holds. Well, if one of these 2 conditions breaks, then we no longer have the strong Galerkin condition G0. So we see right away that G0 is broken. So is this a problem or not? Um, it's not a huge problem, it turns out. Well, let's talk about a couple of properties of this restriction prolongation pair, one of which is kind of surprising, actually. And then the other one gets more close to home with the Galerkin condition. But this one um, is kind of interesting. If I take the restriction operator and I multiply it by the prolongation operator, in this case, in the cell-centered case, and maybe not anywhere else, but at least in the cell-centered case, I get an identity matrix. First of all, we have to ask ourselves, does this product make sense in terms of multiplication? In fact, it makes sense in either direction. So if I could put the P first and I could put the R next, and either way, it makes sense for matrix-matrix multiplication. But in this, uh, if I do it in this order, restriction first and then prolongation second, then I get a square matrix in return, which is NL minus 1 by NL minus 1. Well, the question is, what matrix do you get? And it turns out you exactly get the identity matrix. Kind of an interesting little feature. I'll let you, it's a very easy exercise, and I'll let you guys handle that one. Now, this is the one that's kind of a cute little property. This is the one we're more interested in. So it turns out the standard strong Galerkin condition fails. That is kind of patently obvious already because we know that we don't have a balanced prolongation restriction pair. But it turns out the imbalanced Galerkin condition, assumption G3, does hold. So if I check the wrap condition, I multiply R L minus 1 times AL times PL minus 1. It turns out I get 2 times AL minus 1. So normally for the Galerkin condition, I don't want this 2 to be here. But if you remember back in chapter 5, for the imbalanced Galerkin condition, I wanted the 2 to be there. And we find in this proposition, or at least if this proposition is true, and of course it is, that we precisely get that. So we don't have the strong Galerkin condition, it fails, but we do have the imbalanced Galerkin condition, that is to say, assumption G3 holds. And assumption G3 holds with R equals to a half. So R equals to a half. R is precisely this value in the relationship between the restriction and the prolongation, the transpose of the prolongation. So we called this generically in chapter 5, we called this the value R. And all we said about R is that it should be a number between 0 and 1 strictly. And here we find that it has to be equal to a half. So the imbalanced Galerkin condition holds with assumption G3 with R equals to half. So I'm going to let you check that. It's another easy exercise. And it's even easier if you punch it into MATLAB and just confirm for yourself for a couple of values that it actually does hold. Proving it generically requires, of course, a little bit of algebraic manipulation, but it's also quite easy. But I'll leave that for you as an exercise. Now, we've seen this already back in chapter 5, but I want to emphasize this point again. And in fact, I want to find out the degree to which this failure is real. If the standard Galerkin condition fails and we only have that imbalanced Galerkin condition, we've already seen from chapter 5 that the Ritz projection matrix, the coarse grid Ritz projection matrix, is no longer actually a projection. So maybe it's not fair really to call that a projection matrix. Now, what is a projection matrix? Remember, it's a very special matrix. It's a square matrix that satisfies p squared is equal to p. If I square this matrix, I get the same thing back. It's a very special square matrix that has this property. Well, if that property doesn't hold, then does it almost hold? What are the implications? Well, let's see. So recall that the coarse grid Ritz projection matrix, this pi L tilde matrix, was defined through the Para condition, P-A-R-A. Pi L tilde is equal to P L minus 1, the prolongation matrix, times the reciprocal of the coarse grid stiffness matrix, times the restriction matrix, times AL. So in the present setting, this guy is not a projection matrix. In particular, if you square that matrix, you don't get pi L tilde back, you get 2 times pi L tilde. Well, that's close, but it's not quite, it doesn't give us a prolongate or a projection. So we found whenever the strong Galerkin condition held, pi L tilde precisely satisfied pi L tilde squared was equal to pi L tilde. We no longer have that in this case because we have a 2 there. Okay, so what are the implications of that? Well, there are many. First of all, we cannot at all apply our standard multigrid theory from the early part of chapter 5. We really have to rely exclusively on section 5.9, the very last section of chapter 5. Now, if you find out that a matrix is not a projection matrix, then I minus that matrix is also not a projection matrix because there's an if and only relationship between these two things. So namely, if I have the pi, well, let's do this. Let's do it completely generically. So if I have a matrix P and I find out that P squared is equal to P, square matrix has this property, then I minus P squared also equals I minus P. Okay? In fact, this is an if and only if. It's a two-way street. Okay? Let me write it if and only if like that. Implies and is implied by. So if either one of these is broken, then the other one has to be broken as well. You can't have one holding without the other. Well, this guy fails, so this guy is also going to fail to be a projection. But it's interesting to note what is the square of this matrix. IL minus pi L tilde squared is just equal to IL. All right, now on the other hand, based on our definitions so far and in the present setting, these matrices are still going to be self-adjoint. Okay, so star is the adjoint in the AL inner product. Star is the adjoint, which is the associate to the transpose in the AL inner product. Star is the adjoint in the AL inner product. So they're still self-adjoint matrices. However, they are no longer projection matrices. So it's pretty easy little calculation to show this. If I square the pi L tilde matrix, then based on its definition, it's the par matrix twice. And in the middle, you see you immediately get the wrap matrix, RL minus 1, AL, PL minus 1. But we said that this is no longer equal to AL minus 1, it's 2AL minus 1. So that means we get a 2 out front of everything. But we get to collapse this matrix and that matrix kill each other. Or you could take this matrix and that matrix killing each other. But in any case, you're going to get twice PARA, or twice the coarse grid restriction or coarse grid Ritz projection matrix, the 2 times the pi L tilde matrix. Now again, I'm going to keep calling this a coarse grid Ritz projection matrix, even though it's no longer a projection. So that's just because of historical reasons. We're just going to keep calling it a projection, even though it is not actually a bona fide projection. Right. Now, the other calculations are fairly straightforward to do. Once you know this information, then it's fairly easy to do this calculation. And this calculation, I'm just going to let you check that these two things are true, that they're both still self-adjoint matrices. Those are left for an exercise. But again, I'm leaving you a few exercises to do on your own, but they're mostly just calculations. So they are proofs, but they're proofs just by plugging in and doing the algebra. Now, this one here, I want to emphasize this guy for just a second because I'm going to use this calculation momentarily. So I minus pi L tilde squared is equal to I. Let's think about what is I minus pi L tilde matrix. Well, that's something called the error in the coarse grid Ritz projection. This is the error in coarse grid Ritz projection. So previously we wanted to show that this guy was a contraction. That is, in fact, what you get when you look at the error when you do the coarse grid Ritz projection in certain norms, that you actually get a contraction. Okay, but here this is something weird because it's saying, okay, well, the square of this guy is actually not a contraction at all. It's just the same thing back. Okay, so what this is saying is that we don't get any kind of contraction in a certain sense involving this this matrix. So it's in some sense it's not really reducing an error. But that's actually false because it is reducing the error, but you have to change your norm or change your metric. So I'm gonna show you. Well, not so I won't justify the last statement, but I am going to justify the fact that this is not a contraction in a certain setting. So here's the result. So in the present setting, the coarse level stiffness matrix satisfies this condition here. Remember, 2 can just be put back over there, and so that's just the G3 condition. Well, because of this, it follows that if I take the norm of this vector, I'm just going to get equal to the norm of that vector. If that follows, then it's a consequence of that I L minus pi L tilde in the AL matrix norm is just equal to 1. In other words, this says that this matrix in this matrix norm is not contractive. it's just always equal to 1. It's not contractive, it's always just equal to 1. So it says that the error that you get from using the coarse grid ridge projection in this sense, in this metric, is basically 100%. You're not reducing the error at all. How can we see this? So I've said the proof here is an exercise, but we can do it fairly quickly, just so you can see it. So how would I show something like this? Well, this here, remember, this norm is defined in an operator norm sensor and as an induced matrix norm. So this would be defined as the supremum over all VL not equal to 0 of IL minus pi L tilde VL AL over VL in the AL norm. But this, by virtue of that, is always equal to that, right? So the numerator is exactly equal to the denominator. So this is like saying that supremum is just equal to sup VL AL norm over VL AL norm. So that's the supremum of all the numbers which are exactly 1, which is like saying the supremum is 1. And so that's clearly that norm. So that matrix norm of that matrix is exactly equal to 1. If we can prove this is true. Well, this is true because we lose our projection status that we had before. We lose our projection that we had before. Well, how do we see this? How do we prove this key piece right here? It's pretty straightforward. So we're going to say, we'll call this thing I. So I squared is equal to IL minus pi L tilde VL IL minus pi L tilde VL in the AL inner product. Now remember we said that no matter what, this guy is still self-adjoint, so I can throw it to the other side. Okay, it's still well, no matter what, I can actually throw it to the other side. But when I throw it to the other side, that adjoint just disappears. And so what I get by throwing it to the other side is I get IL minus pi L tilde squared VL VL AL. But now I said in the last result that this guy, when I square it, just gives me the identity. Okay, so that says that what I have is VL in the AL inner product, which is just VL AL norm squared. That proves it by taking square roots. Now, so again, what is it saying? So what it's saying is basically this error has no contraction ability. It's always just going to return exactly the number 1. So if I measure the error, try to get convergence in the AL norm, I'm going to fail. I'm going to fail every time. This is part of the reason why the standard theory isn't going to work for us anymore, because this guy is no longer contractive. Okay. What I mean by contractive is what we would need to show is that this is less than or equal to some gamma which is less than 1. But in this case, that fails. And that throws a big old monkey wrench in a lot of my theory. So that's basically that's what we were doing with this chapter, the latter material of chapter 5, section 5.9. We were really trying to make up for the fact that we lose all of this stuff. All right, so we need some additional multi-level tools. I wish I could come up with a better name for this section. I'm thinking about it right now. Not so great, but it really is additional multi-level tools, which we haven't talked about yet. So tools for moving information from one grid to another. Now, we're going to need this machinery ultimately to establish the last piece of our puzzle, the alpha weak approximation property. We know we have the imbalanced Galerkin condition. Check. Don't need you, Siri. Uh, and this is going to get us to our final goal, the alpha weak approximation property. Before I get there, let me remind you what is our definition of the level L stiffness matrix. It's always good to throw this back up on the screen. The level L stiffness matrix is the same as the usual stiffness matrix, more or less, except that we've got this weird 3 and 3 here. But nicely, the eigenvectors are still nice in this for this stiffness matrix. The eigenvalues are still pretty nice. We can do a lot of things. It just doesn't have a constant diagonal. Okay. So now we're going to define something called the discrete minus Laplacian operator. This one is a little bit weird, I confess. A little bit weird. So you probably said what happened to our piecewise constant functions that we were dealing with way back at the beginning of chapter 7. They're coming back right now. So remember, V is our space of piecewise constant functions. I probably should have copied that diagram from the first slide deck over here just to remind you, but those piecewise constant functions look a lot like our cell-centered functions, except that they have what looks like some additional structure, but it's actually not really real additional structure. So remember, those guys were piecewise constants. All right, actually, there's no more information in a piecewise constant function than there is in a cell-centered function. Cell-centered functions actually have their degrees of freedom right there in the dead center. Okay. And of course, you might say, well, what happened to the ghost cells? The ghost cells are there as well. But remember, the ghost cells usually just pick up the homogeneous Dirichlet boundary condition. So in this case, it's going to be minus that value there and minus this value. So I apologize. It's down close to that blue there. Maybe I could lift that up just a little bit. Actually, let's take it down here. There we go. Now it's bright. Remember, the values of those ghost cell points or ghost cells degrees of freedom is exactly negative of that degree of freedom and negative of that one. Okay, so this is what the space VL looks like. VL. And this doodad right here is actually a piecewise constant function. I guess really technically we didn't define these things to have information outside of there, so can get rid of that. Let's see. Yeah, there we go. Only the cell-centered functions were defined at the ghost cells. But this function here, certainly this interior function, is a type of function that would appear in VL. So let's let VL be an arbitrary function from those piecewise constant functions, and suppose that VL bold is its coordinate vector with respect to a basis. Remember, we had a basis for that space, which was the functions which were piecewise constants and basically 1 on one of the intervals and 0 on all the other intervals. So for example, I'll draw one of the basis functions in green. For example, the third basis function would be this function. So it would be that function right there. Can you see that? So it's 0, then it shoots up to 1, then it goes back down to 0. So that's the third basis function in this set we called BL. So anytime you have a basis, you have coordinates in a basis. And so the coordinate vector in that basis is just going to be the coefficients that you would multiply to get in an expansion to get this function back out. So clearly the coordinates for this function here, okay, for that function which lives in VL, the coordinates are actually these numbers which are the same as the cell-centered values. Okay. In any case, we always have coordinates given a basis. Now suppose that AL is the cell-centered stiffness matrix defined on the previous page, here 3. The level L discrete minus Laplacian operator is the operator minus discrete Laplacian, level L, and this means this superscript means the interior. Um, so why do I say interior? That's because I'm not including anything, any ghost information, any ghost cell information. That'll be my notation always for interior Laplacian. That means basically the boundary conditions are built into the definition of the operator. It's not built in or left as separate boundary conditions. Okay, but you can ignore that for right now. So this operator is going to take a piecewise constant function and map it to a new piecewise constant function. And the only thing I have to do to convince you that this is a good operator is tell you how this works. So here's how it works. I want to take this guy, piecewise, or the discrete level L minus Laplacian operator here, and I want to act on a piecewise constant function and produce a new piecewise constant function. Does everyone agree? That's what I'm doing here. Operator is going to take a piecewise constant function and give me a new piecewise constant function somehow. Well, all I have to do, and all I'm going to do, is tell you how it basically what its expansion is in the standard basis functions from BL. I probably should have said BL is the set of basis function psi I equals 1 to NL. Just remind you, okay? These are the basis functions, and those are going to go right there. So basically, all I'm telling you is what is that new basis expansion, okay? Now, here's where the details are. I'm going to take the vector, okay, from here, which is the coordinate vector with respect to this basis representation for V, and I'm going to multiply that times the stiffness matrix. So take the coordinate vector, grab it, multiply by the stiffness matrix, okay? That gives you a new vector, and basically I can break those vectors into coordinates 1 up to NL. And then those new coordinates I'm just going to use as the coordinates in a basis expansion. So that's going to be the value of this operator. Okay, it's going to give me a new function. I'm going to use these as my coordinates or my in this basis expansion, it's a linear combination. So these are kind of the weights in this basis expansion. Okay, so I hope that you can see that this is a good and true function from VL, right? Certainly it's a linear combination of elements from VL because each one of these basis functions is a piecewise constant function, right? It's stuff that looks like that. Okay, now you might say to yourself, why did you just do that? Why did you waste my time making this definition? It turns out it's like with all definitions, I'm gonna do it in the mathematical sense and give the definition before it makes sense what the definition is for. Okay, so this is the Gauss style. Okay, the Gauss style where I I'm going to build a building, but I'm not going to leave the scaffolding in place. I'm going to remove the scaffolding. And it's not clear what order the building was established. It's just there's a building. Looks nice. So here's a definition. It's not clear why this definition is going to be useful to me, but here it is. I'm going to create something now using that definition called an energy form. Okay, so I'm going to give that the name AL. So the energy form is going to be, turn out it's going to be a bilinear form. Bilinear forms always take two objects from VL or whatever space you're working on. In this case, it's a bilinear form on VL. So you take two functions, one from VL and one from VL, another from VL, and I'm going to combine them, kind of run them through a ringer somehow, turn a crank, and give you a real number out. Okay, so let's make sure that this all makes sense in that setting. So the bilinear form has to be defined for any UL and VL in VL. So this guy is in general different from the first object that I put in. The bilinear form is different than the second one, but I should be able to turn the crank and get some real number. So here's how I'm going to do it. So whatever is the first object, UL, I'm going to apply this operator, which I just defined. Okay, no problem there. So that gives me a piecewise constant function, which I'm going to label, give that label. So actually it's not with VL though, it's with UL here. So apply the discrete minus Laplacian operator to that UL. That gives me a new function, which is also a piecewise constant function. Now I'm going to take that piecewise constant function and I'm going to take its L2 inner product with this piecewise constant uh, function, VL. All right. And I'm just going to use the usual good old-fashioned L2 inner product. Remember what the L2 inner product is. So if I have an F and a G, I integrate from 0 to 1. That's precisely what I'm calling the L2 inner product. Okay, so I take those two things, first one here, second one here, multiply them together, and here's the first question. I have a piecewise constant function, and I'm going to multiply another piecewise constant function by that guy, and then I'm going to integrate over the domain 0 to 1. Does that make sense? Well, the answer is it makes sense as long as when I multiply this guy pointwise times this guy, I get an L2 function in return. In fact, I can do a lot better than that because I know that when I multiply this function times this function, both are piecewise constant functions on this with respect to the same grid, and so the result of that is a piecewise constant function. And every piecewise constant function on the interval 0 to 1 is L2 integrable. Okay? So, or it's just it's even L1 integrable. So when I do that integration, I'm going to get a number out in the end. And so check. This takes two functions, piecewise constant, turns a crank and gives you a real number. And the real number is precisely that. And this is just saying, I put this minus outside here because I can just multiply a minus times a minus. That gives me a plus. Or I could put this minus over here on the other side. It doesn't matter. This is not a symbol. This is actually a minus sign. So I can pull that minus sign, which defines this guy out front. And so that's perfectly legal. Okay, so I've just introduced a weird minus Laplacian operator, which may or may not have anything to do with the Laplacian operator. And I've introduced this weird energy form, which may or may not have anything to do with anything else in the world. But it turns out they are both quite useful, as the following properties are about to show us. First thing I want to say or argue is that this object that I just created is a symmetric bilinear form. Okay, what does it mean to be symmetric? What does it mean to have symmetry? Well, what I mean by symmetry is that for any UL and VL, okay, I can exchange their locations. So instead of having UL first and VL second, I could have VL first and UL second. And that's pretty clear. Actually, that's not exactly clear. You have to really do a little bit of work to show that I could really interchange the orders of these two guys. Okay, but that's true, and there's no problem in doing that. So I'm going to leave that part as an exercise. What else do we have here? I'm claiming also, besides symmetry, we also have bilinearity. That is, we have linearity in each one of these first and second arguments. So I'm going to leave that one to you also to prove. I think that one actually follows quite easily from the definition. And the fact that it turns out this operator here, or I should say this operator here, is a linear operator. And this is a this inner product, the standard L2 inner product is already linear. So using those two properties, you can show that. What else do we have? Finally, for all, actually, this is not quite right here. There's a typo. That should just be 1. Okay, for all coordinates 1 up to NL, or I and j between 1 and NL, okay, AL of the first base or the ith basis function against the jth basis function is exactly equal to the ij coordinate, that is the element in the ith row in the jth column of the stiffness matrix from 3. The stiffness matrix from 3 is just here. So it's either going to be a 3, a 2, or a -1, according to what I and j are, or it could be 0 as well, times HL. Okay. Now this matrix is symmetric, right? So it doesn't matter what order I take I and j. Okay, so that's what we mean by a symmetric matrix. Where the heck does this HL come from? Well, remember, if we go back to 3, we define the stiffness matrix with this 1 over HL prefactor. Where does the HL come from? Well, the HL comes from the fact that we're combining these two objects in essentially an L2 inner product. So we integrate, and so when we integrate, we actually are going to get an extra factor of HL. So if you want, the whole thing is going to, let's see, so this is either going to be, these objects here are either going to be 3, 2, -1, or 0, all divided by, all of those entries divided by HL squared, and then I multiply by HL. So altogether, that's going to be 3, 2, -1, or 0 divided by HL, because I get an HL here and a 1 over HL squared from these entries, and so that leaves me with a factor of 1 over HL. Okay, so that also you can check. This one's this one you can just check by putting in those basis functions. Remember, these are my piecewise constant basis functions that are 1 on certain cells and 0 everywhere else. So put those values in this definition, and you should pretty much immediately get this result. Okay, so I'm going to have to stop there. Let's see, where are we going here? The next object that I'm going to describe in my multi-level tool belt is what's going to be called an L2 projection. So we're going to define this thing called L2 projection, whatever the heck that is. If you've taken a course on advanced PDEs, or maybe taken what is that? No, 547, applied linear analysis. We talked a lot about, whenever I taught that course, talked about L2 projections in there. And so you might have seen these in the context of studying PDEs, maybe in the context of measure theory. Some people have seen them in the context of L2 spaces, etc. In any case, this L2 projection is going to be central to our ultimate goal of proving this alpha weak approximation property. So we're going to need this L2 projection and show that it has certain nice properties. But we're going to stop there for now, and I'll take any questions you guys have.